Hello everyone, good day. So today we'll be discussing another method in solving beam deflections, and that is the conjugate beam method. So conjugate beam method, so technically it is just a transforming of beam. So later on we will understand on why we have to transform a real beam to a conjugate beam. Now, let's understand first how to transform a real beam to a conjugate beam. So all you have to do is to look on the supports or to the end of each beams. For example, you found a simply supported beam or simple support such as hinge or roller. So once you saw that on the end, so if you will try to convert that into a conjugate beam, same pa rin yan. It will be still a hinge and roller. However, for a fixed support, if that will be a fixed support, that will be a free end in conjugate beam. Now, for a support, hinge and roller, which can be found on the middle span or interior support, so if you try to convert that into conjugate beam, it will be an internal hinge. So, however, if that is an internal hinge on your real beam, that will be a simple interior support on a conjugate beam. Okay? So again, no, i- first thing to understand here, you should understand here is how you will convert a real beam into a conjugate beam. So that is very important for this method. Now, let's have sample problem or sample beams to be converted in a real beam. So you have to look on the ends. Now you have here a free end. If you have a free end, that will be a fixed support sa conjugate beam. Now if you have a roller support anywhere in the midspan, that will be an internal pin. Okay. Now if you have a fixed support, that will be a free end. Okay. So again, let's just recall, no? If that is a fixed end, it will be a free end. Now, if that is a free end, it will be a fixed end. So, vice versa lang sila. Okay, so now let's have here a simply supported beam. So, this is a hinge and a roller. So, if you will try to convert that into a conjugate beam, same pa rin. Will be still a hinge and a roller because they can be found at the end. Again, if a support is hinge or roller on ends, it will be still a hinge and roller doon sa end. However, if that is a fixed support, if you will try to convert that into conjugate, that is already a free end. A free end na siya. Then you have a free end fixed dito, it will be a free end again. So, ideally, this is not considered as a beam, di ba? Kasi wala namang support. This is unstable. However, we just want to have a conjugate beam, not a realistic beam. Okay? So again, no, this is not a real beam, it is just conjugate. Now, let's say we have here a fix. Now, let's have this problem, a fix. We are going to convert that. It will be a free and a pin or roller. It's up to you. Same lang naman yan. You just have to identify the vertical reaction for this support. Then a roller at the end will be still a roller at the end support. Okay? So that's it. No? That's how you convert a real beam into conjugate beam. Now, here are the steps, okay, in performing conjugate beam method. So first is to select a reference point. Why do we have to select a reference point? Because we are going to create the moment diagram by parts, just like what you've done on area moment method or moment area method. So number three is to load the moment diagram by parts into conjugate beam. And last one is to create a shear of conjugate beam. Or if you ever saw the force of a conjugate beam, that is equivalent to the slope of your real beam. Okay? Slope of real beam. So, and then the moment of your conjugate beam is the deflection of your real beam. This is the important part of your conjugate beam. The shear is equivalent to the slope of your real beam. The moment of your conjugate beam is the deflection of your real beam. And that's why we convert uh, a conjugate I mean the real beam into conjugate beam. Para for us to solve the slope of a real beam, you just have to get the shear of your conjugate. So, balikan natin yung mga sample. Let's go back to our sample beams and then try to understand the concept of conjugate beam method. So again, the real beam, for real beam deflection or the delta or y, let's say y, let's say the deflection of your real beam is equal to the the moment, no, of your conjugate beam. However, for the y prime or slope of your real beam is equal to the shear of your conjugate beam. Okay, for example, this fixed beam, fixed support. Now we know that a fixed support has a no deflection. So y here is equal to 0. Okay, and then also the slope here is equal to 0. So that means for this point of your conjugate beam, the moment at that point is equal to 0. Obviously, that is a free end. And then the shear at that point is equal to 0. Kasi free end din yan. Okay? So, let's take a look with this. Now, for a point pin support, your y at that point is uh the value of the deflection at that point is equal to 0. Now, if you are going to look on the equivalent conjugate beam, yung moment neto is equal to 0. Okay? How about the slope? Obviously, the slope of that hinge is not equal to 0. Y prime is not equal to 0. Or the slope is not equal to 0. And for conjugate beam, of course, for a hinge support, 'di ba, the slope the shear at that point is not equal to 0. So that's why um if you're going to convert uh the real beam into a conjugate beam, especially for the supports, make sure you satisfy this condition. The deflection is equal to the moment of your conjugate beam. And the slope is equal to the shear of your conjugate beam. Okay, so I hope you now understand how we convert a real beam into conjugate beam. Now let's try to solve sample problem. Okay. Anyway, before we solve sample problem, let's recall first how do we draw the moment diagram by parts. Okay, the important loadings such as the concentrated moment. Take note, if you have a concentrated moment, that is just a rectangular moment diagram by parts. So same with a concentrated moment, uh, which causes the beam to bend negative bending. No, it will bend a negative bending like that. Okay, it will give you a negative area of moment diagram by parts. So for concentrated load, that is a triangular. Okay, triangular load diagram. Okay, so triangular moment diagram by parts for a concentrated load. For a uniformly distributed load, So that is a second degree curve with an area of BH, one third B times height. And then another, same to the other side of your reference point. Anyway, this is your reference point. Now, if you have triangular load, make sure that you are going to create a reference point to the location of the highest intensity of your uniform load. Okay, yeah. Okay, so I think we can now solve this beam, sample problem beam. For this problem, we are going to solve the slope and deflection at point C. So what is the slope and the deflection at point C having the modulus of elasticity of 200 gigapascal and the moment of inertia of 125 times 10 raised to 6 millimeter raised to 4. So first is you have to solve the reactions support. So we have 6 and 11 and 6. So let's just confirm if that is 11 and 6. So let's some moment at B times 10 minus 5 times 4 minus 18. Then a negative moment given by the triangular load, so 0.5 times 4 times 6, and then the distance of 1/3 plus 4. So answer. So we have 9. But 9. So 5 times 4 minus 18, 1/2, 1/3 of, oh, sorry, 1/3 of 6. 1/3 of 6. Okay, so 11. So summing force is vertical. So it will give us 6. Let's say 11 minus of 5 minus 0.5 times 4. 0.5 times 4 times 6. It's 5. And then plus the unknown by 0. The answer is 6 kilonewtons. Okay, now that we already know the support, so we can now draw the first is draw the moment diagram by parts. So first is to select a reference point. So in this case, we have to select this as our reference points because we have here a triangular load which has a larger intensity at C. So start tayo kay concentrated load. So that will give us a triangular load. So for the value of this triangle, I mean for so a concentrated load will give us a triangular moment diagram by parts. So which is the highest intensity will be equal to, just take the moment of this 11 to your reference point. We have 11 times 6. 11 times 6, that is equal to 66. So for the area of this triangular, so we will just get the we'll now get the area of this triangle or pwede naman later pa, no? So for the area of this triangle, so we have na 198. Now let's just confirm if that is 198. So for the area of the triangle, that is 1/2 of 66 times 6. So that is equal to 198. Okay, next is let's identify its centroid of that triangle. Okay, so the centroid of that is 1/3, no, from your reference line. So that's 1/3 of 6. So let's calculate the value. 1/3 of 6. So answer is 2. Okay, so from this point, so that is equal to 2. Next, we have here a trapezoidal triangular load. So the moment diagram by parts of the triangular load is a second degree spandrel. Okay, so from 0 and then to a certain magnitude to your reference point. Then now let's identify uh, the, the intensity of this spandrel load. All you have to do is to take the moment of this triangle to your reference point. So that is, uh, s- sorry, that this spandrel is third degree because we have a triangular load. A triangular load is what first degree. So we have, again, no, the intensity of this is just the moment of this triangle to your reference point. So that is 1/2 4 6. 1/2 of 4 times 6. 4 times 6. So that is equal to, and then the distance is 1/3 of 6, and that is equal to 24. So I just put here negative 24 because the area later of this spandrel third degree is a negative area. Now for the area, so that is negative 36. So let us confirm if that is correct. So again, the area of a spandrel is 1/4 of base times height. Times base, we have base of 6. And then the height of, okay, the height of for 24. So times 24. So answer is 36. How about the its location? The location of its centroid. Okay. We also need the centroid of this area. Just like what you've done on your area moment method. Okay, so we need the area and also it's the location of the centroid of those areas. Okay, so later on you'll understand why. Okay, so what's the location of the centroid of a third degree spandrel? That is 1/5. Okay, 1/5 of your base. So the base is 6 meters. So times reference point. Next is for this concentrated load, 6 kilonewton upward. It will give us a triangular load. Okay, triangular moment diagram by parts. So ang magnitude neto, yung intensity neto class is just the area of the 6 towards point C. 6 times 4 is 24. For this concentrated moment, this is a moment that will tend to rotate your beam upward. So therefore, it will give a positive area. So we have a rectangular. Anyway, before we proceed to that rectangular area, let's just get first the area of this triangle so that we already have the resultant of this triangular area. Okay? So that the area of this triangle is 1/2. So we have 0.5 times 24 times 4. That is equal to 48. Okay, and then the location of its centroid is 1/3 towards point C, 1/3 of 4. So that is equal to 4/3. Then next is this one, no, this concentrated moment. Again, that moment will give you a rectangular area of moment diagram by parts, which is located on a positive side. Okay, so the height, the intensity of this is 18, and then location of the centroid, and then the area of that rectangular is the area. No? You have here see base times height also no 18 times 4, that is 72. The location of that 72 towards point C is half of 4. Okay. Now we are ready to, since we're done with moment diagram by parts, we are now ready to, anyway, this 5 kilonewton don't have any moment diagram by parts because point C is our reference point, and 5 kilonewton don't have any moment towards points. So we're done with the moment diagram by parts, we're ready to draw or convert the conjugate beam, the real beam into conjugate beam. However, this real beam is just a simply supported. Okay? If we have a simply supported, the ends or the hinge is at the end. So therefore, this will be still a hinge and this roller will be still a roller support. And this is now your conjugate beam. We're now ready to solve the deflection and rotation, okay, at point C. To solve the deflection and rotation at point C, okay, the definition of conjugate beam, if you solve the deflection and rotation, The deflection is your moment. Okay? To solve the deflection, you have to solve the moment of your conjugate beam. To solve the slope of your real beam, you have to solve the shear of your conjugate beam. Now, if before we solve the shear and moment at point C, of course, if you only want this shear and moment at that point, you can consider it's either left or right side of your section. So obviously, mas madali if you were just consider if it would be easier if you are going to consider the right portion. So we have to solve the reactions of the supports. Okay, so let's solve the reaction of the support at point B. So let's assume that is a clockwise or downward rather. Okay, so let's sum moment at point A. Summing moment at A, so we have, let's say clockwise is positive. So we have RB times, okay, the distance of 10. So this loads, take note class, the moment diagram by parts now will be the load of your conjugate beam. These are loads. So meaning positive area are positive loads, upward loads. Okay? Downward loads are negative area. The negative area are downward loads. So this is 48. We already get the area of this load. So the resultant of the load is 48, which is counterclockwise to negative. And then we already identified its distance. So this is 4/3 towards point C. However, we are going to take the moment about point A. So 4/3 plus 6. And then 72 is also counterclockwise, so negative. So we treat clockwise as positive for summing moment. So the distance is 2 plus 6 or 8. And this is also clockwise, 17 counter rather 198. So that is negative times the distance of 6 minus 2. Okay, this 36 is okay, the resultant no of the load of this spandrel load. The resultant is 36. And that is clockwise papuntang C. That is plus 36. And then the distance is we have 1.2 towards C. However, we are going to take the moment about point A, so we have 6 minus 1.2. So therefore, RB is equal to 154.72. Okay? So, so we now have the reaction at B, 154.72. So take note class that the reaction at B, so on your lecture in shear and moment diagram. So whatever the value of the reaction at the support on the simple support, if that is the so meaning that is also equal to the shear at that point, shear at B. So now, actually, this reaction at B or shear at B is also equal to the slope of to the slope of your real beam. Okay, slope of real beam of point B. Okay, so nakuha mo na dito yung slope at B. So just get the reaction. Okay, so for example, if the question is determine the slope at B, just get the reaction of the support. And that is automatically the reactions or the slope, okay, at that point. So, however, this is not the question here. The question here is, what is the slope and moment at C of the real beam? So, for conjugate beam, we just have to identify the shear and moment at point C. Okay, so anyway, let's solve also the reaction at A by summing forces vertical. Again, this reaction at A is the shear at A or the slope no of your real beam. The slope at A of your real beam. So if that is the question, you can easily identify yung um if the reaction at A is ay nakuha mo, you can easily identify the slope at A. So let's sum forces vertical. So you have RA, negative RA. RB is downward since as we try to sum forces, so it yields a positive value. So this is downward force. So obviously that will be a downward force because most of your forces are going upward. So let's Okay, so coming forces vertical. So we have negative RA plus 198. So these are the vertical forces, the resultant of your load. And then minus 36 plus 72 plus 48. And then minus DRV is 154.72. So RA is 127.78. Okay? So actually, kahit hindi mo nakunin yung reaction at A, because if you'll just consider this cutting section, since you only want to identify the shear and moment at point C, just cut the section at point C. Consider the ACS section. It's up to you if you're going to consider the left or right. Anyway, that will just give you a same answer. Now let's um consider right and solve the shear at point C, considering the right section. So we just want to draw the shear diagram from right to left. So if you're drawing from right to left, if you are solving from right to left, take note that the value of the shear force that you are going to get here, if that is a if you're going to perform right to left shear diagram or moment diagram, take note that the sign convention should be downward should be positive, and then upward should be negative. Okay. However, if that is from left to right, so upward should be positive, and then downward should be negative. So you just have to reverse the sign convention. Okay. So since we are considering right section, and we are going to draw the shear diagram or to solve the shear at point C from right to left. So downward forces are positive. So let's solve shear at C. Okay, so we have downward force. Positive yan si RB. So 154.72. And then upward si 48 and 72. So negative. Okay, 48 and negative 72. Therefore, shear at this point is equal to 34.72. So that is a positive shear. Okay, so therefore, that is also the shear at point C, a positive slope. Okay, take note, if we have here a positive shear here, that is also equivalent to a positive slope to your real beam. A positive shear is a positive slope. So therefore, sign conversion here is important for you to identify what will be the direction of your moment. So this positive value is also equal to the positive value on your double integration method. Okay, so if this is positive, um, positive is slope. Take note, a positive slope is a counterclockwise motion. Okay, so therefore the slope at point C is counterclockwise. So we now have the slope at C. This value is in kilonewton meter squared over EI. So meaning you are going to apply first, or you are going to substitute the value of EI. So if you are going to convert this into kilonewton per square meter, so the gigapascal should be first in kilonewton per square meter. So let's convert first the value of this EI into kilonewton square meter. We have to raise. Raise to form the numerator and the denominator. Okay, so answer here is 25,000 kilonewton per square meter. Okay, so that is the value of AI. Just substitute here so that we can get the slope in radians. Okay, so I have 34.72 over 25,000, the value of AI. So therefore, in radians, where the slope at C is 1.3888 times 10 raised to negative 3 radians. Okay, so again, that value is
which means, a counterclockwise. Again, a positive slope is a counterclockwise rotation. Now, what is the value of moment at this point C? Considering right section, so take note no for sign convention, counterclockwise moment is positive. If you are going to consider right to left solving moment, okay, or drawing moment. So moment at C. Now, if it will give a positive moment, it means, okay, a positive deflection. Okay. Now, if this will give a negative moment, it means a negative deflection. Positive deflection goes upward. Negative deflection goes downward. Okay, downward to, ito. So let's solve the value of moment at point C. Let's get the moment of this load, RB, and the upward load 72 and 48. Okay, so for RB, that is clockwise, so negative RB 154.72 times the distance of 4. This is counterclockwise, so plus, again, counterclockwise is positive, and the distance going to C is 4 thirds. And then this is plus counterclockwise, 72 times the distance of 2. Okay, so the value of moment at C is equal to negative 410.88. Okay, so meaning we have a negative moment. Now, this moment is a negative deflection. So those units are in kilonewton cubic meter over EI. So meaning we are going to substitute first the value of EI so that it will be in meters. Okay, substituting the EI, negative means negative downward deflections. So we have negative 0.016432.5 in meters, in millimeters. So we have 0. So that is 16. Okay, so 16.425 millimeter or a downward deflection. Okay, so downward deflection. So obviously at point C, it will deflect downward. So just like this. So let's say we will draw the deflected shape of the beam. So this is the deflected shape. The tendency, the lowest point at here because at this point, pataas pa siya eh. Kasi ang slope dyan is upward. Yeah. So the slope here, sorry, is counterclockwise. At point C, the slope is counterclockwise, meaning the maximum deflection might occur at this point. Okay, so conjugate beam method. So anyway, what if the question is maximum deflection? Maximum deflection. Halimbawa, for this problem, we are asked to solve the maximum deflection. For real beam, for conjugate beam, that is the what? Maximum moment. Now, in shear diagram, maximum moment located at what? Value of shear. Zero shear. So, on your real beam, the slope at that point is equal to the slope, okay, is equal to 0. So, all you have to do if you are asked to identify the maximum, all you have to do is to the location. Okay, so point of zero shear. So, identify the point of zero shear. So, obviously, at this point, andun ang point of zero shear. So, some force is vertical and that should be equal to 0. So, that is the point of zero shear. And that, you can now locate the moment, okay? The maximum moment. And that maximum moment will give you the maximum deflection. Okay? So, that's it, no? So, for me, this is the easiest method, conjugate beam method, because you're just solving the shear and moment of a conjugate beam. And that is already equivalent to the slope and deflection. But of course, you cannot do this if you don't have to, you don't know to convert a real to conjugate. So in converting, make sure to look at the supports, Okay, and then the load of your rail beam will not be the load of your conjugate beam. So first is you have to convert or to draw the moment diagram by parts of your rail beam. Then after that, the moment diagram by parts will be the load of your conjugate. So I hope you understand the concept of conjugate beam method. Okay, anyway, let's have another problem. So this problem is a non-prismatic beam. So we will try to solve this using conjugate beam method.
So when we say non-prismatic beam is actually has a varying area, okay, so varying cross section. So for this problem, A to C has larger cross section than C to E. So meaning A to C is stronger than C to E. So 2EI yung given. Okay. So how do we solve this problem? So same pa rin. So first is to solve the reactions at the supports. So for in solving the reactions, okay, so those are 43.25 and 49.25. So make check no if these are correct. Anyway, I already checked that these values are correct. Now, select a reference point where you get where you draw the moment diagram by parts. Okay, so let's use this as our reference since we have here a triangular loop or varying loop. So make sure that if you have a varying load, always select the reference point or the highest intensity as your reference point. Okay, so we will just take the moment of each load to that reference point. So we have 43.25 upward concentrated load. It will give us a triangular load or triangular moment diagram by parts. So for the value of this intensity, that is 43.25 times the distance, force times distance, or that is 42.5. This downward concentrated load will give us a negative area of moment diagram by parts. So let us draw here. So let's say this line, this line here represents the okay, okay this line here, all areas above are positive, below are negative. Then this concentrated load will give us a negative area. Okay, so the intensity of this load is 40 times the distance. So that is equal to 320. Okay, 40 times. And then we have a rectangular load. So let's just make it a rectangular load on this entire length. So just get the moment as this 5 kilonewton per meter to your point T. So it will give us what type of moment diagram by parts. Obviously, that is a spandrel, second degree. Okay, negative yan. Okay, so negative second degree spandrel. So what will be the magnitude here? So for the magnitude, so just take the moment of this 5 kilonewton per meter to your point E. So 5 times 6 times the distance of 3 meters, that is equal to negative 90. For triangular load, this one, it will give us a negative moment diagram by parts. So that is downward. Then a spandrel, which is third degree. Then the intensity, take the moment of this triangle to your reference point, just 1/2 of 15. This is already 15 of height. Okay, 15 times 3. Okay, times the distance of 1/3 times 3. That is equal to negative 22.5. And these are your moment diagram by parts. Take note that your moment diagram by parts will be the load of your conjugate beam. Okay, so let's now convert this or let's now transform this okay, into a conjugate beam. So this is your, anyway, before we transform, let's finalize first our load. or the moment diagram by parts. This is non-prismatic beam. So we have here given of 2 EI, and this one is only EI. Now, if you have non-uniform or non-prismatic beam, make sure to generalize first the value of EI. Since we have we have different values of EI from A to C to C to E. Make sure we are going to generalize first. So what we are going to do, just since we have here a factor of 2 of your EI, all you have to do is to divide this line or this varying intensity by 2. Okay? So we have to identify this height so that we can divide it by 2. So this is 173. So by ratio and proportion, rise over run. Okay, by ratio and proportion, okay, so we have 432.5 over the total length, 10 meters, times rise over run. Run is 4. So that is 173. Okay. So this one is 80. By ratio and proportion, this is 80. So all you have to do is to, okay, so from this line, your wiring load, it will be divided into 2 by a factor of 2. Because actually this is not only moment diagram by parts. This is M over EI. Okay, so this diagram should be M over EI. So you divide the moment by EI by just the factor. So this is 173 over 2, this is 80, or this is 40. Okay, so this is now the moment diagram by parts. So originally, so ito yung height mo, pero ngayon, okay, tanggal na to class. Okay, just remove this height. So this will be now the new intensity of your loadings. Okay, so just like this. Okay, now this load, this moment diagram by parts will be the load of your um conjugate beam. And this is now your conjugate beam. Okay, this is now the new loads. So triangle. Okay, now what we're going to solve here is the slope and the deflection at B, C, and D. Slope and deflection at B, C, and D. For the slope and deflection, anyway, this is your conjugate beam. Okay, the load of your conjugate beam is the moment diagram by parts. So since this is just, okay, this is our beam, simply supported. If you are going to convert a simply supported into a conjugate beam, it will be still the same. Okay, simple supported, hindi nagbago. Okay. So now let's solve the reaction at B, vertical, AV vertical. Take note that the reaction here is not the same with the reaction of the real beam. Okay, or the reaction here is also the slope at A. So we are going to solve the reaction at A first. So because later on, we will cut this section, then just consider this so that we can solve the slope and deflection or shear. Shear and moment lang neto. Okay, identify the shear at moment at that point, and that is automatically the slope and the deflection of your real beam. Pero solve muna natin yung reaction at A. Okay, so let's some moment at point B. Anyway, by taking moment, you have to cut this into rectangular load and triangular load. So the intensity of this is 259.5 because 242.5 divided or minus 173. Okay, so 432.5 bawasan ng 173. Okay, also, we also have here a trapezoidal load. So from 320 of height, it will now be for 320 minus 80. So that is 240. Okay, so let's now sum moment at point E. Summing moment, so counterclockwise. You can use clockwise or counterclockwise as positive. It's up to you. For now, I'll use counterclockwise as positive. So we have IV, so positive times the distance of. Anyway, let's just put here some directions, the direction of the forces. Take note, class, that the negative moment diagram by parts will be a downward force. So these are downward forces. And downward, downward, downward. This is also downward. However, this triangle is upward. Upward, 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 upward. Okay, so downward, 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 downward. Okay, let's some moment at point. So let's some moment at point B. I think this is point B. A pala, sorry. This is point A. Okay. So AV, counterclockwise is positive. AV times 10. And then you have triangular load, 1 half. Clockwise is negative. Okay, so 1 half of this triangle, no? Area of this triangle, 1 half. Okay, upward area to, no? Okay, so 1 half of height. Height is 173 over 2. And then the base is 4. And then the distance is 1/3 of 4. Okay, 1/3 of 4 plus 6. And then next is the rectangular load. Counterclockwise is negative also. So you can see here. Okay, so 173 base times height times base times a distance of 3. Triangular load is 1 half of 259 times 6. Clockwise is negative again. 1/3 of 6. And then we now have the counterclockwise forces. So we treat this as positive. So we have triangular load 1 half of 40 times 2. And then the distance of 1/3 of 2 plus 6. And the rectangular load 80 times 6. And then the distance of 3. And then triangular load 1 half of 240 times 6 times 1/3 of 6. And then spandrel load. Spandrel, the area of spandrel, second degree, 1/3 yan. Okay, 1/3 of 90 times 6 times a distance of 1/4 of 6. And then spandrel again, third degree, 1/4. Okay. Times the distance of, for third degree, that is 1/5. Okay. So that is equal to 0. Shift solve. So we can now solve the value of IAV. If that is positive, meaning the direction of AB is downward force or negative shear yan, di ba? Pababa. Okay. So actually this will not fit on your calculator. So the technique is just solve each term. So solve mo isa-isa yan, each term. Yan. And then para magkasya sa calc. Now, therefore, AV is 251.2875. Okay. So now, since we already have the value of AV, we cannot cut the section and solve the shear at B and moment at B. Like, take note, class, if we are um, drawing or identifying the shear or moment at a certain cutting section, from left to right ang identification natin. Okay, from left to right, the upward forces are positive and then downward forces are negative. Okay, from left to right also, clockwise moment are positive, counterclockwise moment are negative. So this will be important for your moment naman. For shear at B, let's calculate. Okay, shear at B is, so we have downward force here. Okay, so that is negative 251, a 0.2875. So this is 251 downward, 0.2875. Okay, so then we have triangular load. This is upward load. Again, this triangular load is upward. We don't know yet the intensity of this. However, by ratio and proportion, if this is 172 over 2, 173 over 2, this will be 173 over 4, the intensity of this point. Okay, yung height niya. 173 over 4. So, upward yan. So, plus 1 half of 173 over 4 times 2. Therefore, the shear at B is negative 208.038. And that shear at B is also the slope at B. Okay, which is also a negative slope. Again, a negative slope is a clockwise rotation. Okay, clockwise rotation. Since we don't have the value of EI, so just let it like this. Again, that is a clockwise rotation. Okay, so that is a clockwise rotation. A negative shear is clockwise rotation. Okay, or that is a negative slope on your real beam. Next is moment at B. Moment of at B is the deflection at B. Okay, moment of the conjugate beam is the deflection of your conjugate beam. So, um, let's solve the moment at B. So we have AB, counterclockwise is negative, negative 251 times a distance of 2. And then we have a triangular load, um, clockwise towards point B. So plus 1 half of your triangle, 1 half of base times height times a distance of 1/3 of 2. So that is equal to what value of moment? If that is positive moment, that is upward deflection. If negative moment, then downward deflection. Since obviously this will deflect downward because from your real beam, the loadings are all downward. Okay, obviously this will deflect downward. So therefore, the moment here must be negative. And that is equal to negative 473. The moment at B is also equal to the deflection at B. Okay, since you don't have the value of EI, so this will be the final unit. Again, that downward deflection is, or that negative deflection is a downward deflection. Okay? So, next is for the slope and deflection at C. So let's just move the cutting section at point C, the slope and deflection. Okay, slope at C. For the slope at C, it is just the shear at point C. Okay, so just get the shear at point C. Again, downward or positive, downward or negative, downward forces from L to R, left to right. Downward forces are negative, upward are positive. Okay, so ang loading natin dito ay upward forces. We have here upward. These are upward. These are downward forces. Okay. So VC, we have negative 251.2875. And then we have upward triangular load plus 1 half of your base times height. And then the downward is negative base and then the base and the height. Okay, so the answer is a value of negative shear again, no? Again, negative shear is a clockwise. Negative shear is also the value of the rotation at point C, which is a clockwise rotation. Okay? So the rotation here is clockwise. Next is the moment at point C. Just get the moment of this loading towards point C. So we have a 251.2875 counterclockwise toward point C, a distance of 4 meters. And then the distance, then this triangular load, 1 half of 173 over 2 times the distance of 4, the distance of 1/3 of 4. This triangular load, negative triangle. So counterclockwise, negative 1/3 of 2. So the value of moment is equal to a negative 801, which is also a negative deflection. Okay, again, negative deflection refers to a downward deflection. Last one is the deflection at C. For the deflection at C and slope at C, all you have to do is to cut the section or to solve the shear and moment at point Sorry, we are now solving the deflection and the rotation at point D. You have to cut the section at this point. So cutting this section will give us another triangle which unknown ang magnitude. So this is 259.5 by ratio and proportion. Okay, so the total height of this. So by ratio and proportion, so we have 259.5. And then now the height of this triangle, this one. So we will perform ratio and proportion. 259.5 over this length 6 meters times 3. Okay, so times 3. Therefore, the magnitude of this one is 129.75. So we have 129 for this one. 129.75. Okay, for the magnitude of this one. Now, the magnitude of this one, so this is 240. So this is 3, 3. So therefore, I think this will be 120 by ratio and proportion. Okay, pantay lang naman yan. Okay, so now let's, so we're correct. So the total height, okay, so the total height is 129.75. I mean, the total height is 302.75. Okay, so dito naman is 200 for the total height. Anyway, we just need this 120. Okay, 120 for this triangle. And then for this spandrel, so we need ratio and proportion for second degree, and it will yield 22.5. So let's check if that is correct. So by ratio and proportion in second degree, so 290 over 6 squared. Take note, squared ang distance. And then the distance of the other is 3 squared. Answer is 22.5. Okay, so let's now get the shear at point D. Take note, the shear at point D is equal to the slope. Okay, the slope at point D of the real beam. Okay, so let's calculate. So downward, negative. Triangular load, 1/2, positive. Okay, 1/2 of 173 over 2 plus times 4. And then rectangular load, 173 times 3. Triangular load, 129 ang height. 1/2 of 129.75 times 3. Triangular load, negative area. Rectangular load ay negative area. 80 times 3. Triangular, ang height is 120. 1/2 of 120 times 3. And then this spandrel second degree is the value of the value of the area is, or the resultant is 1/3. Okay, so answer the shear at T is 152.8. So that is a positive shear or equivalent to a positive slope for a real beam. And then a positive slope is a counterclockwise rotation. Okay, so this is a counterclockwise rotation. So counterclockwise rotation. Okay, yeah. How about the moment at point D? The moment at point D is also equal to the deflection at point D. So take the moment at about point D. So negative 251.2875. Counterclockwise is negative. Take note from left to right, considering cutting section from left to right, negative. Or counterclockwise is negative. Okay, counterclockwise is negative. Clockwise is positive. Again, for shear naman, upward is positive, downward is negative. Okay, since this is counterclockwise, it will yield a negative moment. So, negative 251.2875 times 7, total distance is 7. Next, we have we have a clockwise. Okay, so these are upward load. It will give a clockwise moment about point D. Okay, so we have the triangular load plus 1/2 of 173 over 2 times 4 times 1/3 of 4 plus 3. And then this triangular load, 170, this rectangular load, 173 times 3 times 1.5. Triangular load, okay, times the distance of 1/3 of 3. Negative area, okay. So, I mean negative, counterclockwise. Okay, counterclockwise. Okay, so this is downward forces. Okay, downward forces will give, so taking moment about point D, it will yield a counterclockwise rotation. Okay, so counterclockwise rotation. So therefore, this triangle is negative since it will give a counterclockwise. Negative 1/2 ng 40 times 2 times the distance of 1/2 of 2 plus 3. Rectangle, counterclockwise then. Okay, so 80 times 3 times 1.5. Triangular, 1/2, counterclockwise then. And then the distance. Spandrel is 1/3 of the air, 1/3 ng base times height. Then the distance is 1/4 of the base. And that's it. That's, again, this is, I think this will not, this will be the moment, okay? Or hindi siya kasya sa calcu. So just get every term. Okay, then the moment at point D is equal to, okay, negative 739 moment. Negative moment is a negative deflection. A downward, okay, downward deflection. Okay, so that is your answer. One moment at, okay, deflection at H. Okay, so that's it for conjugate beam method. So I hope you understand the concept of conjugate beam. So again, no, this is the easiest way in solving deflection reaction. Because you're just solving the moment and shear at a certain point. However, again, you just have to solve first the reactions, or you just have to draw first the moment diagram by parts, and after that, those moment diagram by parts will be the load of your conjugate beam. Okay, so that's it. So thank you guys for uh listening. I hope you understand this topic.